Welcome to this video about matrices. Here's an example of what a matrix is. If you have a bunch of numbers in rows and columns, that's a matrix. The rows and columns are often denoted in the official notation that you'll see on the top, but the one on the bottom has specific numbers. This matrix, for example, is called a 2 by 3. We call it a 2 by 3 because it has 2 rows and 3 columns. This, by the way, would be different than a 3 by 2, for example, which would be reversed. Matrices can be added or multiplied by scalar. In this case, a scalar just refers to a number. For example, if we were adding matrices A plus B, you would just add them component-wise, meaning each element would be added to the corresponding element of the other matrix, and you could get a result. I recommend hitting pause and confirming how easy it is to add matrices. Hit pause now. Matrices can also be multiplied by numbers. These numbers are referred to as scalars because they scale up or down the size of the matrix. So for example, if we multiplied matrix B by 3, we would get this result. I recommend hitting pause and figuring out how I got that. Very simple. Further, we can multiply matrices by scalars and then add the results. This would be called a linear combination and would work out exactly like you would expect it to. Again, I recommend that you stop and analyze the numbers here just to make sure you see how easy this all is once you figure it out. Hit pause now. In addition to adding and effectively subtracting matrices, we can also multiply two matrices together. This is different than the scalar multiplication that you just saw. A minute ago, you saw 3 times a matrix. But we can also multiply one matrix by another. For example, we could do matrix C times A in this case. Now, not all matrices can be multiplied, but it depends on the number of rows and columns of each of the factors. This particular product is doable because we're multiplying a 4 by 2 times a 2 by 3. Why would a 4 by 2 be multipliable by a 2 by 3? Because of the rule that the inner dimensions must match. And by the way, when they don't, you can't multiply them at all. And when they do, the result is determined by the outer dimensions. So this matrix, these two matrices, when multiplied together, will yield a 4 by 3 matrix. Now let's go through the particular steps, same problem here, to show you how to multiply matrices together. First, you multiply you do what's called a dot product between the first row and the first column. A dot product, which the reason for that name is strange and we won't go into, but a dot product is where you multiply the first number in one vector by the first number in another, add that to the second number in one vector times the second number in another, plus, if there were these, they're not here, the third number times the third number plus the fourth number times the fourth number, and so on. And this product here, if you work it out using PEMDAS, which of course is what we use, you would get an answer of 2. And because we had used the first row and the first column, that gave us the first row and first column in the answer. The second number in the resulting matrix would be 6, which comes from this. Notice that the 6 is in the first row and second column of the answer. Not surprising that it came from taking the dot product of the first row and the second column in the factors. Likewise, the third number turns out to be -4. This number is in the first row and third column of the answer and corresponds to the dot product of the first row and the second column of the factors. And you continue this, and I recommend as I go through each one that you hit pause, analyze the numbers before you hit play again. Here's the next one. Here's the next one. And so on, so on, and so it goes. We're going to now do the last row of the resulting matrix. I'll say again what I said earlier, just in case you missed it the first few times. The 13 in the answer is placed in the fourth row and the first column. It came from taking the dot product of the fourth row and the first column, respectively, of the two factors that led to this product. Here's the next one, hit pause to analyze. And here's the last one. That is essentially how you multiply matrices. Remember, not all matrices are multipliable. They have to have the exact matching dimensions. In other words, restated, in order for two matrices to be multipliable, the number of rows of the first matrix, let me start that sentence over. The number of columns in the first matrix has to be equal to the number of rows in the second matrix. Let's add another concept here called the transpose of a matrix. Here's a 3x3 matrix called B. The transpose of a matrix is where you convert rows to columns and vice versa. Here's the transpose, often written as B with a T above it. Notice the first row of one is the first column of the other. The second row of one is the second column of the other. And likewise, the third row and third column equal each other. Just a matter of transforming rows into columns and columns into rows. That's what a transpose is. Next, let's talk about the inverse of a matrix. I'm going to eventually teach you how to find the inverse of a matrix, but before I do, let me tell you what it means for two matrices to be inverses of each other. This is not a how-to moment in this video, this is just an idea moment. What if we were to multiply matrix A and B together? Well, we would use the method that you just learned on how to do that. This would end up being the result. There is lots and lots of work that went into this, and I will not show it here. If you're still unclear how to multiply matrices, rewind and watch, and then try to multiply these matrices together. In fact, I recommend doing that and seeing how it was that I arrived at this answer. But how I arrived at it is less of the point than what's special about the answer. The answer is called an identity matrix. By definition, an identity matrix is any square matrix with ones on the main diagonal, meaning from the upper left corner to the lower right, and zeros in every number that isn't on the main diagonal. That's the identity matrix. Now, what are inverses then? In this case, A and B are inverses of each other. Any two matrices are inverses of one another if their product is the corresponding identity matrix. In this case, we would either say that A is the inverse of B or that B is the inverse of A. And we denote that with an exponent of -1. But it's worth noting here that that is not really even an exponent. But don't think of it as raising something to the -1 power. Rather, just think of it as the notation that indicates that one matrix is the inverse of the other. The real issue, though, is how do we find inverses? It's a very complicated process for finding the inverse of a square matrix. In most classes, including if you're in mine, you have to be able to find the inverse of either a 2x2 or a 3x3 matrix. Finding the inverse of a 2x2 is super simple, and you could easily look up a formula for that. So we'll focus here on the more difficult 3x3. To find the inverse of a matrix, there are several steps you have to go through. The first step is to replace each element in that matrix, each of these 9 numbers, with its so-called minor. Let me show you what I mean by minor. Crossing out the first row in the first column leaves us 4 numbers. These 4 numbers could be placed into a 2 by 2 determinant. And if we calculated the value of that 2 by 2 determinant, we would get negative 15. Oh, by the way, if you need help on finding determinants, you should have already watched that video before you got to this one. But if you haven't, go back and watch that. Let's proceed. Next, we'll cross out the first row in the second column. That again leaves 4 numbers. Turning those 4 numbers into a 2 by 2 determinant and computing that determinant yields 10. Next, we'll cross out the first row and third column, taking the 4 remaining numbers and computing their determinant. And you continue to do this. Now we'll cross out the second row and first column, yielding a determinant of 3. If you're not sure why the determinant is 3, the work is shown near the top of the screen, negative 5 minus negative 8. But you may want to go back and watch a video on 2 by 2 determinants. You continue doing this. I recommend hitting pause each time and doing the work yourself. Here's one more. Hit pause and verify that that actually works out to 1. Hit pause for this one. Work it out. Same here. And same here. So now we're on to step 2, where we multiply each element by either positive or negative 1. If you're a little confused by the I and the J notation here, what this means is that we multiply, if I is our row and J is our column, we multiply each element in this by negative 1 to the I plus J. And if that's still a little confusing, just remember this pattern of alternating plus and minus signs with pluses in the corner. If we multiply positive or negative 1 times each of the elements in this matrix, this is what we get. Now you'll notice the numbers in yellow are highlighting. The 10, 3, 1, and 4 change to negative 10, negative 3, negative 1, and negative 4, whereas the other numbers didn't change at all. Now, don't misunderstand what's happening here. I'm not turning all the numbers into negative. I'm reversing the signs on all the numbers. It just so happens that 10, 3, 1, and 4 are positive, and then therefore they all became negative. You might mistakenly think that I've made all the numbers negative here. No, I didn't. I just changed those 4 special numbers, which happens to be the only positive numbers. Next, we take the transpose of the matrix. That just means we turn rows into columns and columns into rows. And once you've done that, the last step is to divide each element by the original determinant. Now, the work isn't shown here, but the determinant of A turns out to be 3. There's lots of work that went into that 3, but if you're still wondering how to find a determinant of a 3 by 3 matrix, go back and watch that video. You will see that this has a determinant of 3. And after you divided by that and simplified, this is your inverse matrix compared to the original matrix. Note, not all matrices have inverses. Why not? Well, for 2 reasons. One, it has to be a square matrix to have an inverse, generally speaking. And secondly, sometimes the determinant of a matrix is 0 instead of 3 in this case. And if those red 3s were all zeros, how would we divide them all by 0? We couldn't, right? So note, not all matrices have determinants. Not all matrices have inverses. Now, the reason for finding inverse matrices is that you can use matrix inverses to solve systems of equations. At this point in your studies, you've probably solved systems like this using substitution, or maybe elimination. Maybe you've seen Cramer's rule, or maybe the Gaussian elimination, or maybe all of those, depending on the course and the order in which your teacher is teaching linear equations. This video we'll conclude with this problem showing you how to use matrix inverses to solve a system of equations. The first thing you do is turn it into a matrix equation. And you can see that here. You essentially factor out all the variables into a 3x1 matrix, x, y, z. Now, to solve this equation for x, y, z, it turns out all you need to do is find the inverse of the coefficient matrix with the 9 numbers in it, and multiply that by the constant matrix with the 3 numbers in it. You'll notice these are the same 3 numbers that started out on the right side of the equation. And if you use that very lengthy process that you just saw to find the inverse of this matrix, I will not show the work here, but rewind the video to see how, or better yet, try it yourself. And if you were then to multiply those two matrices together, if you forgot how to multiply matrices, rewind further back and you'll see how. The end result turns out to be a 3x1 matrix, which, lucky for us, is the exact answer for x, y, and z. And now I've used matrix inverses to solve this system of equations. And as long as the system of equations has a single solution, as this one does, you can use it. You can use the inverse method, as shown here, the matrix inverse method, to solve for x, y, and z.